Welcome to Gravity's Greatest Experiments, a 20-slide tour from simple observations to modern discoveries, delivered by Dr. Microlearning. Over the next few minutes, we'll trace key experiments that shaped our understanding of gravity, set expectations for visual highlights, and invite you to think like an experimenter as we move from idea to evidence. Here, we summarize Newton's three motion laws in plain language, using the slide's illustrations to show inertia, force-producing acceleration, and action-reaction pairs. Think of these as tidy principles that turned anecdote into predictable mechanics. And notice how the diagrams compress each law into an everyday mental image you can carry forward. The Pisa demonstration captures a pivotal moment where Galileo favored observation over authority by dropping different masses to show they fall alike. The crowd illustration reminds us how public experiments can shift opinion from skepticism to awe, and how a single clear test can prioritize empirical evidence over long-standing dicta. Contemporary critics blamed air resistance for Galileo's results, so the inclined plane became the clever follow-up to dilute gravity's effect and time motions precisely. This slide shows how controlling variables, anticipating objections, and reproducing results are core experimental habits that isolate the true gravitational behavior from confounding factors. Cavendish set up a delicate torsion balance inside a quiet shed to measure the tiniest attraction between indoor masses, effectively weighing the Earth for the first time. The diagram highlights thin wire twists and lead spheres, and underscores the patience and precision required to detect the weakest force known at the time. Zooming in on Cavendish's method, the torsion balance converted tiny torques into a numeric value for the gravitational constant g, enabling a planetary mass estimate within 1% of today's value. This is a tidy example of quantitative elegance, where a small tabletop measurement unlocks huge cosmic information. Einstein reframed gravity not as a pull but as space-time curvature, and the trampoline analogy helps make that intuition visual. Mass dents the fabric. Light and objects follow those dents, and curved paths replace straight lines, shifting our language from forces tugging to geometry guiding motion. Eddington's 1919 eclipse expedition brought theory to observation by photographing starlight deflected near the sun, matching Einstein's prediction of a 1.75 arc-second shift. The story combines wartime logistics and careful measurement, showing how a clear experimental test can transform a bold idea into accepted science. Gravitational waves turned theoretical ripples into audible signals, with LIGO's twin observatories detecting a black hole merger, CHIRP. The slide highlights dual 4-kilometer arms, simultaneous detections in Louisiana and Washington, and the astounding engineering that senses motion 10,000 times smaller than a proton, opening a new window on the universe. Repeated gravitational wave detections are building a cosmic census, moving from solitary chirps to statistical population curves. By collecting many black hole and neutron star events, we begin to map mass distributions, merger rates, and formation channels, turning individual discoveries into demographic knowledge about the universe. The Event Horizon Telescope stitched radio dishes around the globe to produce the first silhouette of M87's black hole, turning an abstract horizon into a visible ring. That world-sized camera demonstrates how global coordination and clever imaging convert theoretical shadows into concrete measurements that confirm gravitational predictions. Exploring quantum gravity takes us beyond horizons into extreme tests where event horizon interiors, Hawking radiation, and information loss raise fundamental questions. This slide frames Frontier Labs as places to probe thermodynamics of spacetime and to develop next-generation theories that reconcile quantum effects with gravitational singularities. The unification quest pits smooth spacetime against discrete quanta, exposing conceptual clashes and failed early attempts at simple gluing. These failures motivate new, background-independent frameworks that try to recover both relativity's geometry and quantum mechanics' discreteness, reminding us that new ideas often follow from confronting clear inconsistencies. Two leading approaches, loop quantum gravity and string theory, offer contrasting core claims about space and particles, while sharing the same scientific aim. Both currently lack definitive observational proof, so the field progresses through pluralism and theory development, seeking ways to remove singularities and recover known physics in tested limits. Looking ahead, gravitational wave detection will grow through upgrades and new locations, from cryogenic mirrors and longer Earth-based arms to lunar seismometer concepts, hunting low-frequency waves. The slide suggests how site choice and technological improvements together shape sensitivity, enabling us to pinpoint sources and extend observational reach across cosmic scales. Quantum sensors use ultra-cold atom interferometry and precision freefall to map tiny gravity variations, and ongoing miniaturization aims to turn lab-scale systems into portable gravimeters. Applications range from monitoring ice mass and aquifers to civil engineering inspections, showing a pathway from advanced physics to practical geodesy and infrastructure health tools. Modern smartphones contain accelerometers and gyroscopes that let learners replicate historic determinations of g with surprising precision. The makeshift pendulum experiment on this slide shows real-time data logging and automated timing, collapsing the lab to classroom gap and empowering students to measure local gravity within small error margins. Educators can tap public datasets, guided Jupyter tutorials, and semester projects to bring frontier gravity science into classrooms without costly equipment. This slide highlights accessible strain curves and radio-viz data, step-by-step notebooks to convert raw numbers into audible chirps or shadow images and project ideas that foster hands-on scientific participation. Gravity's grand narrative traces a path from a falling apple to planetary laws, black holes, and the quantum foam, illustrating scale-invariant curiosity at work. The slide emphasizes rigorous testing and global collaboration as enduring themes that transform simple questions into deep cosmic understanding and collective scientific progress. Finally, the Gravity Challenge invites you from spectator to contributor. Jot down an unanswered question, map campus or online resources to pursue it, and nurture the small observation that might spark the next breakthrough. With curiosity and a bit of structure, anyone can join the chain of discovery that drives gravity science forward.